and to thank all of you for staying this late for, let's say, a different lecture. So, my first question to you is, when you are about to enter a new domain, how do you research it? Someone? ChatGPT, thank you. So this is the current late 2024 answer. So I would like to offer an alternative. It's Mike talked about the lifetime of papers in the LLM domain. So this is based on the work from early 2023, God forbid. And hi, I'm Yuval Feinstein. I've been doing NLP and search engines for a very, very long time. And including currently I'm working with several clients. One of them is Anydish, a company startup doing giving you an app with healthy recipes, which you can adjust to match all sorts of health conditions and culinary preferences. And the common theme of everything I do is converting text into structure. And we'll see more of this in a way. So one of the ways we can enter a new domain is use a universal phenomenon. Just a minute. So about a year ago, more than a year ago, I wanted to visit Georgia, the country, not the state. And the problem was that I knew almost nothing about Georgia. And in the same time, I was following on LinkedIn someone called David Knickerbocker. He's a software engineer residing in Oregon. And he had several series of publications. One of them was 100 Days of Networks, another was 100 Days of NLP. So our first phenomenon we'll look at is networks. And the nice thing about networks is that networks are everywhere. Show of hands, how many of you came by train today? Okay, less than I hoped, but let's say few people. And the Israel railway map is an example of a network where we have nodes that are the stations, and we have edges, which are the railway lines. The first published example of networks was Euler's solution of the Königsberg Bridge problem. The problem was, can you go over every bridge in Königsberg? Well, you go over it only once, and Euler found a negative result and gave us network theory in return. So, in network analysis or social network analysis, we have nodes. Nodes represent entities, and edges represent the relations between the entities. And we'll use networks for insights. Now, I don't know what domains you work in, but I'll bet many of you can use networks in their problems they work on. Now we'll get some inspiration from a book called The Possibility of Violence by Dror Mishani. This is a suspense novel. There's a detective, a couple sitting at the beach, and this says that in every investigation, everything is sunk in darkness or fog, but after some time, the connections are clarified, and the picture always goes clear. In the darkness, a new point of light suddenly turns on, and it illuminates the others as well. So our points of lights, my interpretation, are nodes, and the connections are edges. So another ubiquitous phenomenon is text. You find text everywhere, and we'll use text to build networks and to go deeper into existing networks. We'll find entities and relations to get nodes and edges. The problem of finding entities in text is called named entity recognition, and the problem of finding relations in text is called relation extraction. Now, my plan today is to start with a domain, to build a network from it. Next, we'll investigate the network using divide and conquer. And last, we'll do a deep dive into what we find. Now, in order to build a network, we need a data source. Our chosen data source is English Wikipedia. Depending on the domain you're researching, your data sources may vary. You may choose others. Wikipedia has a very simple translation into a network. We'll start with several seeds, which are Wikipedia pages. I want to learn about Georgia, so the pages will be related to Georgia. We'll call a few steps, and we'll get a network. Okay, so here is my expert illustration of crawling Wikipedia. We have the red spiders. Every spider stands on a Wikipedia page, and we'll walk a few steps on pages that are linked from this page. And let's see. Well, okay, courtesy of Shlomi of Arpilai, we can view the code here. I'm using the Wikipedia package, which is a Python incarnation of the Wikipedia API. I'll just show you. Basically, we start with a few pages. The pages I chose are Georgia, Tbilisi, the capital, and several other places in Georgia, and tourism in Georgia. And I'm creating an edge list. So in order to get an edge list, I start from my seed places, and I call search wiki. Search wiki it gives me a number of pages which are linked from the original page. And we get a list of pages, and surprise, surprise, we'll build a data frame. And let's see it in the presentation. Okay. So our edge list every edge has a source and a target. We have almost 3,000 pairs of source and target, and every source and every target is a page. And we get this beautiful network. Can anyone guess the professional term for this kind of network? Let me hear you. No wrong guesses. Dark hole, nice. I call it a hairball. We cannot get that much insight from a hairball, so we need to go deeper. We need to divide and conquer. We need to focus. So, how do we divide and conquer a hairball? First, we identify important nodes. Hopefully, important nodes will give us interesting topics. Now, what are interesting nodes in a network? I claim that one way to find an important node is to identify central nodes, which shifts the question to what is central. There are centrality measures, basically functions, which go over the nodes in a network and gives us a number. The higher the number, the more central the node. So we'll use two centrality measures, PageRank and betweenness centrality. First, PageRank. PageRank was the defining algorithm of Google. It was invented by Larry Page and Sergey Brin while they were at university. And it looks at a network. And here we have the nodes A, B, C, etc. Every node casts a vote. The more and the more important are the nodes which point to your node, the higher rank the node gets. And this is done iteratively for some stages. And we get here like the most important node is B, because it is linked to by other important nodes. Next is C, and so forth and so on. Okay, let's look at betweenness centrality. So for the 5 people who came here by train like me, did we come to a central train station? So I'm looking at 2 train stations. One is Dimona. It's over down here in the southeast. The other one is nearby Rakevet HaShalom. Now, I define betweenness centrality as the ratio of the paths going through the node to the overall number of possible paths. So the only paths going through Dimona are of trains which eventually reach Dimona. So Dimona is not so central in the rail network. On the other hand, Hashalom is almost every north-south train goes through Hashalom. Also some this weird east-going path, I think it also goes through Hashalom. So Hashalom is very central according to betweenness centrality. Now, let's go back to the Georgian network. We'll use the networkx library for most of our calculations today. And let's see some code. Okay. So first, I'll show you. We read a data frame, and next we create from it a network. NetworkX has a from pandas edge list function, which creates a graph or a network from a data frame. And next we run PageRank, just over our network. And we get here the nodes sorted by PageRank. We'll show this in a minute. Also, we calculate between a centrality in a similar fashion. And okay. So what did PageRank give us? It gave us Georgia, which is fine, Tbilisi, which is okay, and the next nodes are kind of strange. List of renamed places, economy of Georgia, Jude the Apostle, and it goes worse from here. So PageRank didn't give us such great results. And let's continue. Between a centrality is better. It gives us Georgia. It gives us Stepantsminda, which is a village in the north of Georgia, which is one of my original seed nodes. It's good. Tbilisi, Mount Kazbek, which wasn't one of my original nodes, but it is a famous tourist site in Georgia, and tourism in Georgia. Overall, this is better. Now, another way to look at an important node is to look at its ego network. Ego network means I'm taking the node and every node directly connected to it. We call this node the ego node. The other ones I call the alter nodes. And I look at the relations between the alter nodes. So I can see here that, for example, we have Parliament of Georgia, and it's directly connected to gambling in Georgia. Go figure. We have Caucasus area and Godauri, which is a monastery, I think, in Georgia. It's good. It's
It's also ski resort.
Ski resort. Yeah, it could be better known. Yeah. Okay. So this is a way to look at the central nodes. Okay. Another way to look at the full network. Up until now, we looked at important nodes or central nodes and their immediate surrounding. Say we want to say something about the whole network. We'll use an algorithm called K-core, which is like peeling an onion. I start with an external layer of the network. I remove it. Then I remove the next layer until I keep the middle of the layer. Now, the external layer is nodes that are connected to anything. The next layer are nodes that are connected to one other node. The next layer is nodes connected to two other nodes. And you can see here the procession here. So the 0 core is the original network. 1 core I remove the gray node. Next, I'll remove the ones with one connection and the ones with two connections. I'm left with the 3 core, which we could say is the essence of the network because these are connected to many other nodes. So remember our friend, the hairball. I ran the K-core algorithm 5 times. I'm left with the 5 core. And we have a beautiful structure here. We have 2 main components. It's hard to read. I'll read it to you. The right component is about Tbilisi. Here we have all things about government of Tbilisi, the seal of Tbilisi, the flag of Tbilisi. And on the lower part, we have Liberty Square, and we have Tbilisi railway station, Tbilisi airport. So sites or places in Tbilisi. On the left component, we have Georgia, demographics of Georgia, religion in Georgia, Christianity in Georgia, flag of Georgia. So it gave us a nice partition between Tbilisi-related pages and general Georgia-related pages. Okay. And we also ran PageRank again. So PageRank improved for the 5 core. We have here Tbilisi Metro, Geography of Georgia, Flag of Georgia. And the between us somehow is worse than it was, so no problem. And another way to look at networks is to look at communities. What is a community? Community is a set of nodes which are connected heavily to one another and less connected to other parts of the network. And the most popular community detection algorithm is called Louvain. And we ran Louvain. We get this community structure. Every color is a different community. I chose sample community number 2, which is, as we all know, the third community, because we start from 0. And this community describes the Feinstein and this Trinity Church. It's a nearby church and nearby national park. So this community is about places. It would be nice if I could say it's about places nearby Stepan Smithstar, but it isn't. I ran Google Maps and found this place is actually far away, but it's nice. It gives us another insight into the network. And okay, so far we look at the network through important nodes. We looked at communities. We looked at ego networks of important nodes. We looked at the K-core to get an insight on the whole network. Say we found an important node, and we want to go deeper. We want to research what are the characteristics of this important node. So how do we research things? Ideas?
ChatGPT, Claude.
Okay, this is anywhere but this lecture. What we do in this lecture is networks. So we'll build another network. Now, how do we build this network? In order, say I want to go deeper into Tbilisi, and I want to build a network representing Tbilisi. We already had this the left side, I think, right? No, the right side of the two community of the K-core, but now I'll just look inside the Wikipedia page for Tbilisi. I'll bring all the text from it. I have this slide here. Okay, I'll get all the text from the Wikipedia page. I'll find entities using the spaCy library. I'll build edges between every two entities that appear in the same sentence. And then we'll have a network, and we know already what to do with a network. So let's see. So this the part of the API gives me the text, the content of the Wikipedia page about Tbilisi, and I give it to spaCy. It's called NLP. I run NLP on this text. I run entity extraction, and I get entities of these types: person, org, and GPE, namely people, persons, org are organizations, GPE is a location, something like geographical, physical entity. Okay, so after we extracted entities, we get a list of lists. Every list has the entities in a single sentence. So for the first sentence, it's Tbilisi, Georgia, Tiflis. Tiflis is the old name of Tbilisi. For the third sentence, we have the Russian Empire, the Caucasus Viceroyalty, and Tiflis. And then we build edges for these combinations of entities, like Tbilisi, connecting Tbilisi and Georgia. And can we see the network? Oh, hooray. Beautiful. A beautiful hairball. So what do we do next? We go again and we look for central nodes using PageRank. We get Tbilisi, Georgia, University of Georgia, etc. And the real nice result I got from this network was by using K-code. This time K equals 6. Again, I'm testing your eyesight, so I'll explain the components. So this one is Prague, Cologne, Czech Republic, Olympic Palace, Germany. We have Milan. Any ideas as to what this region?
Twin cities?
I don't think it's Twin Cities. I think it's related to soccer, like Milan and the Olympic Palace. And so, okay, here we have Azerbaijan, Armenia, Bolshevik. I don't know why, and Russia. These are neighboring countries, most of them. Here we have Tbilisi Circus, Palace, Parliament. Again, these are sites inside Tbilisi. Here we have many universities. I believe all of them are in Tbilisi. And this invisible cluster, because it's so heavily printed on, these are neighborhoods in Tbilisi. So purely from network means, from this not so sophisticated visualization, we got a nice division of Tbilisi into subjects. So, what we described today, we wanted insights of a new domain. So we chose data, we built a network, we dug deeper into the networks through interesting nodes and subnetworks. We made a deep dive into specific nodes using NLP. And hopefully we got some insights. As I said earlier, this is all inspired and based on David Knickerbocker's work. He wrote a book, a textbook, Network Science with Python. He has a wonderful blog and a GitHub repo. We used these Python packages, networkx, spaCy, Wikipedia API. Also, somehow Scikit network got in only for visualization. Another inspiration of mine is Asaf Shapira. He's a local guy. He has a great podcast called networkx about network science, about social network analysis. You can hear it in English or Hebrew as you choose. And there are several no-code tools for handling social network analysis. That's it. Any questions? Yes, indeed.
Do you think we can use NLP for embeddings such that would basically mirror the structure of the network, would be conditioned on it?
The question was about using embeddings to get the network structure. There's actually a third field called graph neural networks, which basically does this. It encodes a network into embeddings based on the relation between nodes. And people do interesting stuff with graph neural networks. I haven't studied it that much, but this is one direction which could be very useful. Another such direction is graph databases, which use the network structure in order to store and retrieve data. Okay, more questions? Yes, David.
Can we somehow use network analysis to infer the type of relationships? For example, if we have some ontology made of triplets.
Let me see if I understand the question. If we have an ontology built of triplets and you convert it into a network.
Yes, can we go the other direction also? If we have a network, can we somehow cluster not the nodes but the edges and get the
Can we cluster the edges? I think we can. I haven't done this, but it's again a nice direction. The nice part about what I showed today is that it was very much syntactic. Like I used the network topology, but I didn't know anything about the nodes other than the topology. What you're suggesting, I think, is semantic, and that we will classify different edges. I guess we could classify edges based on the related topology. For example, maybe here we could find out somehow that an edge connects to neighborhoods because it's densely packed. I don't know. It sounds to me a bit hard because we don't know that much about the edges. Not sure. Okay. Yes.
Thank you for your lecture. You gave a very intuitive example of your trip to Georgia. It was very clear, but I wonder how this is actually really used, I don't know, in real products today. What is actually examples of usage?
Okay, so I'll say David Knickerbocker again. And he actually built a company based on this research. He started out as let's call it a DevOps guy or a network engineer. And he used this kind of networks in order to migrate servers. If you have a server that is built upon one script which calls another script, and calls a third script, and so forth and so on, you can build a network of scripts and then migrate them based on the network properties. Another example, I think I can stand here for 10 minutes and discuss about domains I know very little about. So one of them is biology, like protein-protein interactions, and then I think I saw Dan offer here earlier, but basically you can model interactions between molecules as a network and find interesting stuff. I think that the limit is your imagination.
Yeah, immediately you use it in order to calculate who is the most important target to kill in the terror. Right?
Yeah. Actually, in David Knickerbocker's book, he gives a very similar example of, say you want to destroy a network. Which node do you target? And which Jenga brick you pull, and you make the most epic fall. Yes, it's a good example.
So
Epidemiology, yeah, like it's a different perspective to look at problems. Okay. Thank you very much. בטח.
דיברת על טקסט פרינט והאלגוריתם השני של הסנטרל לסנסור.